I have you loud and clear.
Hello. Welcome. Science.
And that is to say, physics,
medicine,
nature, or
Space. Time.
the brain, life,
The universe.
This week, we're taking a spin around the electron. How does a fridge magnet stay stuck? And how can quantum physics help us in battling cancer? We'll be finding out.
Plus, in the news, the chemistry of breaking down microplastics, exploring bacterial infections resistant to last-line antibiotics, and we're going back to school PE lessons. I'm Izzy Clark.
I'm Katie Haylor, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, hearts. Researchers from Carnegie Mellon University have developed a way of 3D printing components of the human heart, which could be beneficial considering there are around 7.4 million people in the UK with heart and circulatory disease. The parts are made of collagen, the main structural protein in our bodies, and they work just like real heart tissue.
Printing collagen has been a major hurdle in biomedical engineering, but now the team has made a big leap forward. Andrew Hudson, one of the lead authors on this paper, spoke to Phil Sansom.
A group of biomedical engineers at Carnegie Mellon University have been working on something amazing: 3D printed bits of human heart. It's all thanks to their special 3D printing technique called FRESH.
FRESH stands for Freeform Reversible Embedding of Suspended Hydrogels, and this is a technique that's pretty powerful in that it kind of allows us to 3D print fluids.
That's researcher Andrew Hudson. He says the reason it's helpful to print a fluid is that you can print collagen. Collagen is a protein, the most abundant protein in our bodies. Some have called it the holy grail of bioprints, and it's very difficult to 3D print.
Even just printing really any length scale of any material or any geometry from collagen has been very, very difficult for the field.
That's because to get collagen into a useful gel form, you have to print it when it's still a liquid.
And if you were to just try and 3D print that in air, it would collapse on your build plate, you'd end up with a puddle.
People have tried to solve this by solidifying it with gelatin, but the end result isn't very natural. The FRESH technique takes a different approach.
We 3D print inside a tub of support material, and that support material has a really important physical property in that it has what's called a yield stress. And what that means is there's a minimum amount of force that you have to exert on this material, and then it starts flowing like a fluid. It's very similar to mayonnaise, where if you turn a jar of mayonnaise upside down, it doesn't slosh to the bottom because it has a yield stress. But whenever you can scoop it out with your knife, you can spread it on bread, because at that point you're shearing it enough so that it can start flowing like a fluid. So what we're printing into has that physical property, and that's what allows us to inject material into it and then have it be cushioned and prevent it from collapsing during the printing process.
This support material, the lab's own secret sauce, is what they've really improved in their recent paper. They've been able to 3D print at much higher resolution by making the particles of the support material smaller.
And you can think of it really much like drawing a picture in the sand at the beach. So if you try and draw, say, the Mona Lisa in gravel, you can't get as much of a high-resolution picture as if you were to try and print in fine sand. Now, in that analogy, the precision with which I can move my hand is just dictated by how expensive is your printer and what hardware do you have. The thickness of my finger is just analogous to the width of my needle. And then what is the most important part, which is what we've improved upon in this paper, is reducing the size of those particles to try and therefore get a higher resolution picture that we're trying to print layer by layer.
With this fine control, they can print all sorts of structures, from cylinders to networks of tubes that are like arteries and veins.
So in the paper, what we had done, we had taken patient-specific data from someone's heart arteries, and then we merged that and we kind of computationally filled in some gaps. And so we have this really interesting structure that's combined of patient-based data along with computationally generated tubes.
They can even 3D print a custom heart valve.
Notably, we made the first proof of concept functioning heart valve. And there's a huge market in terms of heart valve replacement, heart valve repair.
At the moment, there are two treatments to replace heart valves. You can either get mechanical ones or bioprosthetics. The mechanical ones are often metal and can be really well engineered, but there's a high risk of blood clotting, so you need to be on blood thinners for the rest of your life. Bioprosthetics might be from a pig or a cow, and you won't need blood thinners, but these don't last nearly as long.
We can kind of combine the best of both worlds with bioprinting, where we can, in theory, have engineering design and all the criteria that we can simulate before we build anything first, but we can print it from the materials that we know that we like from bioprosthetic valves that are very blood compatible. It's obviously a very long 10 plus year regulatory pathway, but we're really excited to try and actually do patient-specific bioprinted medical devices.
Andrew Hudson and his colleagues see a massive scope for this fresh 3D printing technique.
What's really powerful about our technique is that we can use it on printers that cost around $1,000. The current bioprinters go from a bare minimum of $10,000 up easily to $1 million. And what I think we show very convincingly in our paper is that the hardware that you have does not matter as much as how you print these things. And we're really showing that with just a $1,000 3D printer using the fresh technique, you can outperform a $1 million printer. So it's very realistic to have any university, even high schools, start to have bioprinters. So we're really driving down the cost of bioprinting and really trying to get more people into this space so that they can innovate.
Some really exciting work. So you might have to wait a decade, but then your own heart valve printer. Andrew Hudson there from Carnegie Mellon University speaking about his study in the journal Science.
Now, recently, the issue of microplastics has never been that far from the news. They're tiny bits of plastic from a few millimetres in diameter to even nanometres that can be washed away from everyday objects, including cosmetics and clothes, or can be from larger pieces of plastic breaking down over time. Because they're so small, they aren't easily filtered out by our current sewage systems, meaning they can end up in the sea and can cause issues in the marine world.
Now, scientists from the University of Adelaide in Australia have announced a new catalyst that they hope can speed up the breakdown of microplastics in an environmentally friendly way. And Keita and Urban spoke to Liliana Fruk from the Chemical Engineering Department at Cambridge, who wasn't involved in the study but took a look at the paper for us.
So in this paper, the authors have designed a new catalyst. So they speed up the reaction. So they made a catalyst which is a hybrid between carbon nanotubes and manganese compounds. And manganese is a chemical element which is known as a catalyst in many chemical reactions. So by designing this catalyst, they have shown that they can actually use it to degrade microplastics. And when we think about degradation, that means not kind of cleaving it into the smaller pieces, but really degrading the chemical structure. This is, of course, an interesting approach.
So you said it was a carbon nanotubes.
Yes.
Are these just really small tubes of carbon?
If you imagine a very, very, very thin layer of carbon, if you would bind this into the tube, then you will get a very small nanotube. In their case, it was several hundred nanometers in length of these carbon nanotubes.
We can put a catalyst in to speed up a reaction. So does that mean that the reaction was going to happen anyway and we're just speeding it up?
You know, in general, there is nothing in the nature that stays the same. So eventually the plastics would degrade. It just takes thousands of years. So you would like to speed it up. So what they've shown in paper is exactly how the plastic structure changes over 6 to 8 hours. Eventually they say that you can degrade the plastics into CO2, carbon dioxide, and then this carbon dioxide could be used by marine organisms in the photosynthesis, for example, if you have a plankton to produce a biomaterials. So I think the plan with some of these new strategies is basically to use them in sewage water treatment plants. And if you have a combination where you have one reactor within this plant with microorganisms, then the products could be used to create a biomass. So you would have a circular system.
So these catalysts are described as springs. Mm-hmm. Why is the shape of that important?
For catalysis, the surface is important. So if you have a spring-like surface, you are introducing different curvatures so that the molecules can fit in, but you are also increasing the surface amount that is available for catalysis. So it's much better to have a curved surface than, for example, just a planar one.
These springs are also magnetic.
Yeah, so having a magnetic materials is, of course, very useful because you can imagine that you throw this catalyst into a mass of water. So how are you going to get it out? One way of getting it out is to use magnetic force. So you basically use a big magnet where you remove your catalyst when the reaction is done. So you first recycle your catalyst and you ensure that the catalyst is not ending up in the drinking water.
So do you think we'll be using these kind of catalysts in sewage treatment plants anytime soon?
Although this is an interesting concept, it will take a while until this is practically usable, because one issue is the production, scale up of these materials. And the other thing is, of course, there needs to be a certain time which you invest into studying the biocompatibility. You would not like anything to leak out into the water what is maybe more toxic than the plastic itself.
For now, do you think we should just use less plastic?
Well, one of the biggest things is that dealing with plastic would require changes in our lifestyle. This whole hype about microplastics is relatively recent, but I think we first also need to focus on the other plastic waste, because even if we deal with the microplastics, there will be new microplastics produced from the plastic waste we have. So there needs to be changes in policy making, but also in the personal relationship to plastics.
That was Liliana Fruck commenting on a paper by Zhan Kang and his colleagues at the University of Adelaide, and it was published in the journal Matter this week.
Hi Katie, how are you?
I'm pretty snug, to be honest. Quite cosy in here.
The Naked Neuroscience podcast explores the workings of the brain and the nervous system in our bodies and beyond.
It does not mean that you need to be sophisticated on an instrument. You can just hack on a piano.
Wow, so I can legitimately tell my friends to shut up because I've just passed my driving test.
You have my blessing, yeah.
Do you want to know who you are? Can we actually understand how we think?
From lifting the lid on consciousness to remembering how to forget, join me, Katie Haylor, each month as we make connections with scientists and spark up conversations on the latest neuroscience news. Listen and download for free at nakedscientist.com/neuroscience or subscribe to Naked Neuroscience wherever you get your podcasts.
On the way, we're putting physical education to the test and later on exploring what have electrons ever done for us. We've got a demo coming up, so grab yourself some strong sticky tape to join in at home.
Now, Klebsiella pneumoniae is what's known as an opportunistic pathogen. It's a bacterium that can cause infection in vulnerable people, resulting in skin, blood and respiratory problems. News this week reveals that strains which are resistant to a group of so-called last-line antibiotics, carbapenems, are spreading through hospitals in Europe. And once these last-line-of-defence drugs no longer work, there's little else left.
In fact, the estimated number of deaths in Europe due to these antibiotic-resistant infections increased from about 340 in 2007 to about 2,000 in 2015. Sophia David and her colleagues set out to better understand this spread. They analysed the genetics of 1,700 samples taken from patients in 244 hospitals in 32 countries across Europe, which were collected during an earlier study.
So the key finding from our study is that the majority of carbapenem-resistant Klebsiella pneumoniae infections in Europe were a result of transmission within hospitals. And we also showed that transmission between hospitals, particularly those that were close by and in the same country, also played a significant role in the spread of these bacteria.
And is it correct then that you can infer those relationships because you know about the relatedness between these different strains?
Yes, exactly. So where we find that two samples are very closely related in terms of their genetic code, and they also originate from patients that were treated in the same hospital, that gives us a very strong indication that transmission likely occurred within that hospital.
So why are these carbapenem-resistant strains of Klebsiella pneumoniae spreading through hospitals?
Within hospitals, a relatively high usage of antibiotics creates a selection pressure whereby the bacteria that are the most resistant to antibiotics will be the most likely to survive in this kind of environment.
Ah, so they're the fittest, essentially.
Exactly, so that they are the fittest in this type of environment.
These strains that are spreading between people, would that suggest that perhaps hygiene or infection control may be partly a cause?
Yes, exactly. So the finding here suggests improving infection control, hygiene measures, more carefully monitoring patients when they get referred from one hospital to another. Those sorts of measures could have a key impact. I should emphasise that the number of infections with these very resistant types of bacteria are still very low.
How long does it take before you would be sure that somebody has a carbapenem-resistant strain of this type of infection?
So typically it would take a hospital probably a few days from taking a sample from a patient and then getting a result back from the lab. That really is a goal within the community, is for the development of rapid tests that instead of taking days, we could get a result within hours. And it could be that whole genome sequencing will play a major role here. But at the moment, we still need to grow the bacteria in a lab. That's really the major limiting factor before we can then go and do DNA sequencing.
In terms of immediate implications, there's the infection control side of things. We need more antibiotics, I guess, new ones coming through the pipeline. Longer term, could you envisage a situation where a hospital are already aware of the top 5 antibiotic-resistant strains to watch out for in any given week, for example?
Yes, exactly. So instead of there just being a small number of sequencing hubs, as there are at the moment, I envisage these being much more widespread, and indeed hospitals being able to undertake their own sequencing and analysis. Yes, indeed, they will be aware of the circulating strains in their area and will then be able to, for example, flag up new strains that they haven't seen before. So there is still work to be done in order to get to that point.
Let's hope we get there soon. Sophia David from the Wellcome Sanger Institute, and the study was published in Nature Microbiology.
Now, from the joys of freshly baked bread to the lows of burning plastics, us humans get a lot from our sense of smell. But other animals, like dogs, rely on their noses so much more. So why might that be? And why did we evolve to have the noses we do? Well, new research in Science Advances sheds some light on those questions, and Darren Logan from the Waltham Centre for Pet Nutrition joins us in the studio to chat about it. So, Darren, that freshly baked bread, how does that smell get from the environment up into my brain for me to recognise it as a delicious croissant or loaf of bread?
So our sense of smell is essentially a chemical sense. So the volatiles that's coming off the freshly baked bread into the atmosphere is what we're sensing through our sense of smell. And every time you take a deep breath in, the volatiles will rush through your nose and hit these molecular receptors on the surface of your nose called olfactory receptors, and they exist in olfactory sensory neurons. And in a human nose, we have about 300 different types of these neurons, and each one detects a different combination of small molecules. And it's the combination, the pattern of those together that your brain interprets as the smell of, in this case, freshly baked bread.
300 doesn't sound like an awful lot. So how do we end up with the incredible amount of smells that we're able to recognise?
So that is the sort of the real trick of the olfactory system. So it's due to something called combinatorial coding. So each receptor, each of the 300 receptors, can detect a combination of different molecules, and each molecule can activate a combination of different receptors. So when you multiply those together, we think that we can detect up to 1 trillion different odours.
Okay. So how did you analyse smell in this study? What were you interested in?
So we took a advantage of a particular quirk of the olfactory system, which is that each sensory neuron in the nose expresses just one olfactory receptor. And so because we knew that, we were able to use something called RNA sequencing to quantify the RNA of each receptor, and that allows us to tell us the number of each type of neuron in the nose. So you might expect that of the 300 neuronal types, they'd all be equally represented. And what we found out, that wasn't the case. That a very small number, actually, about 10 or 15, are very, very highly represented in the nose, and the vast majority are relatively lowly represented.
So what does this mean then? What do we take away from this?
So we were really interested about what these receptors are these neurons are that are there in very high abundance. And so what we did is we looked at what those neurons are detecting. And what we found in the case of humans is that they're detecting what we call key food odors. So these are the odors that are produced by our food. So as you mentioned, the odors in freshly baked bread. When we looked in other species, and we looked in mice, rats, dogs, and a number of primates, we found that wasn't the case. And likewise, when we looked in mice, we found that the neurons that were very abundant actually detect pheromones, so cues that the mice use to sexually communicate with each other. So what we think that means is that each mammal has evolved to have a nose that is very specific to its niche.
Can we take from that sourcing food is particularly important to us, but there may be other equally pressing matters for other animals? Or how would you pick that apart?
Yeah, that's our hypothesis. There was a theory that our senses of smells are essentially not under evolutionary pressure. They're just drifting around and they can detect anything that we happen to run into. What this research, we think, suggests that's not true, that actually our noses are tuned and over time have been tuned to the things that are important to us to promote our reproduction and our survival. And in the case of humans, our sense of smell is particularly important for detecting food and scavenging for food, and that's why we think our noses are tuned the way they are.
So more receptors equals better smelling ability. Is that pretty much right?
So this is a bit of a mystery in the olfactory field. Species like dogs or mice, or indeed elephants, who we think have the most receptors, may be able to smell more, but we actually think at the moment that it's likely that they don't smell more, they just discriminate better. So they can tell subtle differences between things that we as humans, who are not the best smellers in the world, probably couldn't.
Having said we're not the best smellers in the world, I've got to say, I name myself the bloodhound of the Naked Scientist office because I feel like my sense of smell is really good. Why would that be? Why would I be better at smelling than, say, Izzy, for instance?
Well, there is people who are better at smelling than others, and it's probably down to genetic variation. We know there is a lot of variation in the olfactory receptors. However, we also know that people who are often deemed or described as better smellers are often more verbal, so they're able to describe the smells that they detect better, and that appears that they're therefore better, but they're actually better at explaining it.
Okay, I'm still going to take credit for that one. Very briefly, what's the next step then with this particular piece of work?
So we're doing two things, I guess. One is that we are looking to spatially identify the position of the neurons in the nose rather than just the abundance of them. And this is important because when you smell, the air rushes through the nose, and depending on which parts of the nose it hits, we might think it works differently. And secondly, we are particularly interested in those abundant neurons and finding out exactly what they detect.
We'll have to watch this space then. Darren Logan, thank you very much.
Now, physical education. Some of us loved it at school and some of us didn't. But what's the best way to encourage fitness amongst school children? One study this week is questioning the beneficial impact of a specific test called the bleep test.
This fitness pacer test, also known as the bleep test, is a multi-stage aerobic test that gets more difficult as it continues. The running speed starts off slowly but gets faster after you hear this sound. The aim is to run 20 meters before the next bleep goes off. On your mark, get ready, start.
Fitness tests in PE classes are a staple to physical education worldwide. This process sets out to test your fitness, but amongst kids, it stands as the ultimate assessment of how cool you were during your adolescent life. Ignoring popularity, the actual point of these tests is to introduce an active lifestyle to kids and to hopefully help them improve their less developed areas of fitness. But despite the numerous types of fitness classes employed in schools now, there has been a decline in overall physical fitness. Because of these dips, fitness classes are now a controversial topic in the health and fitness world, which is causing two arguments within school education. Drats. I'm out, coach. Go ahead, shut it down. Whew. As I was trying to say, there is a huge deal of controversy with these fitness tests. There are health organizations and academics that endorse their use in schools because they provide such great surveillance information for physical fitness levels of youth across the globe. However, there's a second camp of academics that argue the tests lack validity, are misused, and are potentially harmful to the students participating, creating negative experiences toward physical education, which could ultimately lead children to participate less in PE and then become less active overall. To get to the bottom of this, a study published in the Journal of Physical Education and Sport Pedagogy looked at 273 students in America aged 11 to 14 who participated in varying fitness tests. These included the pacer, push-ups, crunches, and a test to sit and reach for your toes. The team of researchers from the Taylor and Francis group looked at the associated attitudes and emotions of the students after participating in each test. To accurately record the attitudes of the students, a 5-point scale ranging from agree to strongly disagree was used, combined with a questionnaire that focused on the students' enjoyment, anger, and boredom towards PE. With going through all the responses of the students, the team found that the fitness tests actually have little to no impact on whether students are enjoying PE class. And with a sex distribution of 52% male to 48% female, the team found that certain tests left varying impressions between the two sexes. Specifically, improved performances over time in the pacer test was more important amongst teenage boys, but teenage girls didn't seem to care if they did better. Adding to that, improved performance in the sit and reach test was reported as being more important to teenage girls, while the guys didn't really care if they improved. The major discussion now is to see how the time used to conduct these fitness tests can be better integrated into more successful and influential healthy living techniques for teenagers. One potential solution is to introduce a more refined fitness education curriculum. Even if we find a solution to fill in the educational gaps, there is still this common factor thought to deal with. Everyone hates crunches. Between both the boys and girls in the study, the crunches test caused, and I quote, higher rates of anger toward PE. So even if we see a more rigorous physical education program in the future, we will still be able to confidently conclude together that sit-ups are in fact the worst.
I agree. Sit-ups are awful. Good for you, I hear, but it's not my favourite thing to do. That was Matthew Hall summarising that study published in the journal Physical Education and Sport Pedagogy. And if you'd like to find out more, all the transcripts and papers can be found on our website, nakedscientist.com.
Now, we've just got time for a look at the Naked Scientist mailbox this week, and Randy Honier has been in touch via the website, and he asks, how can I tell the difference between gold and pyrite? So we spoke a little bit about this when in June we did our extremely deep show and we went down into a gold mine. So we've got gold and we've got pyrite. Pyrite is what is called fool's gold. It's iron sulfide. And there are a couple of tests that we can do to find out what the difference is. So colour is one. They've both got a brilliant metallic coating, but the difference is the tones in yellow. So gold is the sort of golden to silvery yellow, whereas pyrite a really brassy yellow. The shape as well, you sort of get gold in nuggets, some small flakes, whereas pyrite will probably come in quite big chunks. It's quite rare to find that small cubic gold lump, as we might see in films. There are also some physical tests depending on how precious this metal is to you. So its hardness, you can scratch a little bit of the material with a blade. If you rub off any loose powder and the mineral has been scratched, then it's probably gold, as gold is much softer than pyrite and it can be cut. But if you don't want to scratch it, then give it a bit of a rub and it should smell, if it's iron sulfide or pyrite, it will probably smell like rotten eggs. So try that one at home, Randy, and let us know how you get on. And if you've got a question like Randy, then send it in to chris@thenakedscientist.com and we will take a look.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions. This week, we're taking you for a spin around the electron. Electrons are tiny negative particles which are, well, everywhere. They're responsible for making all our electronic gadgets work, and they're the reason that a magnet can stick on your fridge against the gravitational pull of the entire Earth.
We'll be attempting to create lightning in the studio, using an electron microscope to look at a bee, and finding out how this humble particle is paving the way for new computing technologies and helping us to tackle cancers.
But first, let's take a step back in time. The word electron, in fact, comes from the ancient Greek word for amber. If you rub a piece of amber, you generate static electricity, and it's a bit like rubbing a balloon on your head. Some Greek physicians even suggested putting electric eels on your head to cure migraines. I wouldn't suggest that, but it was an early version of electrotherapy. But although we've known about electricity for a while, the electron itself wasn't discovered until 1897. Ankita and Urban took a trip to the Cavendish laboratory in Cambridge to uncover how this came about.
We've come to the Cavendish lab, which is where J.J. Thomson discovered the electron. And we're walking down this corridor, and there's lots of portraits of people in the Cavendish. And we're slowly going back in time. Lots of men in suits in the 20s. And the first one is 1919 with Professor Sir J.J. Thomson right in the middle.
We walked through the museum until we came to a case which held a glass tube. It was about the length of my arm and maybe twice as wide, with large bubbles along it. This was the famous cathode ray tube, used in the discovery of the electron. You might remember old TVs, with huge boxes at the back. These held cathode ray tubes that were used to generate the images on the screen. And in fact, even today, we still use cathode ray tubes to produce X-rays. I spoke to Katie Duncan from the Department of the History and Philosophy of Science at Cambridge about how they work.
So if you've ever seen a neon light, this is very similar to what these sort of gas discharge tubes are. They tend to be long glass tubes with an electrode at either end. One of them is positive and one of them is negative, and you connect them up to a battery. When you put a voltage across it, whatever is in that tube, they found that it would glow. And that's essentially what a cathode ray tube is.
So how did cathode ray tubes come about? J.J. Thomson made his famous discovery of the electron in 1897. What did we know about electrons, or rather, I should say, electricity, before that?
The 1800s was kind of a period where we see understandings of what we can do with electricity massively increase. So we could develop formulas and ways to manipulate it, and we could use it, such as the electric telegraph. But what electricity actually was, people didn't really know. There were understandings that there were two kinds of charge, but how that kind of manifested wasn't really known. Whether that was an electrical fluid, two electrical fluids, it was all really quite up in the air. At the time, lots of physicists were interested in finding out about the electrical conductivity of gases at low pressure, because usually in air, electricity doesn't travel anywhere. Otherwise, we'd be electrocuting ourselves all the time as we walked through the atmosphere. If you had a low pressure tube that you filled with gas, you could actually put a current across it. So this is what they were investigating. The electron just happened to be something kind of almost an accident, if you say.
How do you discover the electron by accident?
When he was experimenting with this tube, he took it to a very, very, very low pressure, which is something that other physicists at the time had been trying to attempt. And when he did this, he found that there was a shadow that was being cast behind the anode, so the positive end, which indicated that something was travelling in a straight line from the negative end to the positive end. And the bits that weren't hitting the anode were hitting the surrounding glass and glowing. So he investigated what this ray was by putting an electric field around it and a magnetic field around it, and also examining how much heat that this ray itself was generating. And he used a Lorentz force law to calculate a mass to charge ratio.
Electricity and magnetism are two sides of the same coin. And the Lorentz force is a law which links the two. It states that if you place an electric particle in a magnetic field, it will be deflected at an angle. The amount of deflection depends on the charge and the mass of the particle. By measuring this deflection, J.J. Thomson could measure the charge-to-mass ratio of the electron.
And in doing so, he found that this mass was 1,000 times smaller than the size of the smallest known atom at the time, which was hydrogen. So this started to make some interesting questions about whether there was something smaller than the atomic, whether there was something subatomic.
So he effectively discovered that the atom, which we had previously thought of as the fundamental unit of matter, something that couldn't be broken down any further, was in fact made up of even smaller particles. How did that fit into the existing theories of the time?
Well, there were lots of different theories at the time. J.J. Thomson didn't actually call what he found the electron, he called it a corpuscle. And he believed that this corpuscle was in fact the only subconstituent of an atom, and he devised what we know now as a plum pudding model. So these were small, hard electrons that existed in a sea of positive charge, and they could move around freely, and then they could be made to leave this plum pudding model under the presence of something like a high electric charge. And that's what we saw in the cathode rays.
But the usual picture of the electron today is not like a plum pudding. Most of our science textbooks now describe electrons as orbiting the nucleus of an atom, a bit like planets around the sun. So where did this theory come from?
That was only a few years after Thomson came up with his plum pudding model. Thomson had a student called Ernst Rutherford, and he undertook a few groundbreaking experiments, the results of which didn't actually fit with any theory that the physicists at the time had. Rutherford demonstrated that atoms were actually the mostly empty space model that we know today.
Rutherford did this by firing tiny positively charged particles at a gold foil. He found that the vast majority of the particles made it through, and only a handful bounced back, and this led him to believe that most of the atom was in fact empty space, with a small positive nucleus in the middle and a cloud of negative electrons circling it. And this is a model that's still taught in schools today. Science is rarely simple, and not everyone at the time accepted this model.
It took a good number of years for the scientists to kind of come around to the idea that it was indeed a particle. So it went through this very kind of fluid definition in the early 20th century before it became what we recognise as the electron today.
That was Katie Duncan from the Department of History and Philosophy of Science in Cambridge talking about the discovery of the electron.
So most of us probably don't have cathode ray tube TVs in our living rooms anymore, but electrons are still very much a part of our lives. If you've ever gotten a spark from a nylon jumper that's because of a static electricity, it's actually the same physics as a lightning strike. Now we're joined by Alex Thom, a chemist at the University of Cambridge, who's going to try and create some mini lightning right here in the studio. So, Alex, you've brought some sticky tape with you. What exactly are you planning to do with it?
So I'm going to demonstrate a process called triboluminescence, is where you create light from mechanical force. And so I've got a roll of sticky tape called duct tape, and we're going to need to turn the studio lights down just to be able to see what's going to happen.
Izzy's just about to do that now.
So, yes, if you're going to try this at home, you'll probably want to be in quite a dark room at night time and get your eyes very used to the darkness. So I'm basically just going to peel this tape and we're going to watch for some light coming out from where the tape meets the roll. Any light visible there?
I mean, I'm not 100% convinced I saw anything. I hate to I hate to be the bearer of bad news. Is it not dark enough?
It might not be dark enough in the studio. Unfortunately, there's quite a lot of light in here.
I was going to say, we tried our best, but even when we're recording, it's still quite light. So, yeah.
Okay, so say you did have a dark room. Say it's night time, you're at home, you've turned the blinds down, you turn the lights off. What's actually going on?
So you see a little band of blue light, and that's where, as the sticky tape comes apart from the roll, electrons are caught on one side or the other. So an electron gets stuck on one side and leaves a positive charge on the other. And as you pull that further away, that electron gets further away from the positive charge and eventually zaps back to the other side of the roll and emits light during that process.
So by moving electrons around, we can result with light?
Yeah, that's exactly the same as you get in lightning, in fact.
Ah, okay. So can we create a different frequency light then?
Yes, so the conditions you do it in change the type of light. So it turns out if you do this in a vacuum, you can generate X-rays at the same time.
Wow.
And so there was a team of scientists in 2008 who did this, and they had an automated unroller, and they generated X-rays and actually took an X-ray of a finger using sticky tape.
So that was moving electrons apart, which we're going to take your word for it, results in light. You've also got a banana and some salt on the table. So what are you planning to do with this? I'm hoping it's not some sort of odd snack.
Alas, no. So I've got here a banana, which is in fact a miniature particle accelerator. And
what?
Yeah. So this banana sitting in the studio is generating 15 electrons a second, creating them effectively, which is very different from what we did with the tape, which was just moving them around. So inside the banana, there's quite a lot of potassium atoms, and some of those potassium atoms are unstable, and they decay to a more stable nucleus, which is calcium, and in that process, they give out an electron.
And it's the electrons that you're detecting on the yellow box, which I'm pretty sure is a Geiger counter.
Exactly, yes.
Right, it's got its very own mic, so I'm going to turn that
Excellent.
up.
So hopefully. So this Geiger counter, I'm going to point at the banana and we're going to see if we can detect these electrons being created as we speak. Every time an electron gets into the detector, it will give a click. So it's currently pointing at the air and not clicking very much, hopefully.
So if we just take a listen. Nothing. No, there's not a lot there.
Under maybe, one every 3 seconds or something like that. So
is that what you would expect? Because there is a background level, right, of radiation.
Yes, so actually this is a significantly lower level of radiation than in my house. Exactly, which is rather nice. It's probably because of the walls here.
So there's not very much going on in the air that is around us right now. So question is, what happens when you put the detector on the banana? This Geiger counter there's a yellow box, as I said, and then there's a cable and something which looks like you've wrapped it in foil. Is that the actual detector?
Yes, so there's a tube called a Geiger-Müller tube that I wrapped in foil to try and reduce the background getting into this tube. Yeah.
And what's happening inside that box then? How does the detector work?
So every time an electron goes into the tube, it sends a shockwave of electricity through the cable into the box, and that just converts it into a little click. And I've got a little readout here, and I can tell you how many clicks per second there are.
So you've got a little dial or something, a gauge.
And it's currently less than 1.
Okay, that's reassuring. So let's see what happens with the banana then.
So as we point it to the banana,
there's a couple of clicks, not a lot.
Yeah, I'd say it's about the same. It might even be slightly less.
Why would it be less?
So this banana is actually shielding the radiation that's coming from the studio, and because it's sort of more dense than the air.
Okay. All right then.
So yes, it turns out this banana isn't sufficiently radioactive for us to detect. Thankfully, in a way, it's not quite got enough concentration of potassium.
But you said a banana is a particle accelerator of sorts.
Yes, so it's these potassium nuclei inside that are actually firing out electrons at over a mega electron volt. This is pretty fast, actually. It's a big fraction of the speed of light.
So the other culinary item you've brought with you is some low sodium salt. So if it's which you just spill on.
So there's still quite a lot of low sodium salt here.
Okay, enough for the experiment, right?
Yes, yeah.
So if it's low in sodium, does that mean it's high in something else?
Yes, so they replace the sodium in the salt with potassium so as to avoid you getting high blood pressure, I think, when you eat it.
Okay. So it's this potassium we're hoping might change the game a little bit.
Exactly. So this is the most concentrated source of potassium I think I could find in the home. So I'm going to put the Geiger detector onto this salt and we'll have to listen carefully. So here we go.
That's definitely more frequent. What's the reading?
The reading's about 3.5. So that's quite a lot more.
And how did that compare to the banana, roughly?
The banana was about half.
Oh,
I think,
okay.
yes, yeah.
Okay.
So.
Now, it's not just things you'll find in the kitchen that are radioactive. What kind of other radioactive sources exist?
Yes, there are quite a lot, even some around the home. So in your smoke detector, there's americium, which is used to detect whether or not there's smoke in the air. And that doesn't give out electrons, that gives out alpha particles in that case, which are helium nuclei.
So considering that bananas aren't very radioactive, we don't need to be worried about having too many bananas and having a radioactivity issue?
I think you would be unable to eat that many bananas. A truckload of bananas might just set off a radiation detector, but it's still perfectly safe. You get far less from exposure to that than you would, for example, by taking a transatlantic flight.
Okay, so Izzy, we don't have to worry. The Naked Scientist snack time is all right, safe.
Thank goodness. That's what I was really worried about.
Thanks so much, Alex. Alex Tom from the University of Cambridge. And look out for the X-ray video he mentioned earlier in the show, as we'll be posting it on our social media. And thank you, too, for the Geiger counter as well.
Still to come, more on the Electron, and we're raining down on monsoons for Question of the Week.
And now, let's go into the lab. Today, electrons are an important tool in scientific research. Electron microscopes use beams of electrons, rather than of light, to take images with very high resolution. This means they can be used to look at things in huge amounts of detail that we can't see by eye. They've allowed us to see how tiny viruses look and can even be used to image individual atoms.
And we sent out a message on our social media to ask what you, our listeners, wanted to see using an electron microscope. Listener Hamish Symington replied, suggesting that we look at a bee. So Naked Scientist Adam Murphy took a trip to the materials department at Cambridge to meet Hamish and put a bee into a scanning electron microscope.
I've brought some bees along. These are bees which I've been working with which have died of natural causes after we finished the experiment. And we can have a look at some of the things which make the bees really cool.
But before we could put the bee into the microscope, we needed to do some sample preparation. Because we're firing electrons into the sample, it's important for the sample to conduct electricity so that the electrons can pass through. If the sample's an insulator, the electrons will just get stuck in the sample. A bee doesn't conduct electricity very well, so John Walmsley, a senior technical officer in the Department of Materials, explains how to get around this challenge.
For the samples we're looking at today, they've been coated in a very, very thin layer of metal to make them electrically conducting. Gold is the favourite because it's very nice and stable. It doesn't tarnish and oxidise in the air. In this case, we've used platinum, but it tends to be a heavy, stable metal.
With the sample prepped and ready to go, we approached the microscope. It was a large box, about the size of a dishwasher, connected to a series of tubes and pumps and warning labels, with a small drawer at the front. Simon Griggs, a technician looking after the microscope, opened up the drawer and placed our bee onto the stage.
You slide it onto the stage so we can move it around in X and Y, and we can tilt the stage as well, which is good. And it's in the right orientation for me to do so. So we've got nice bees there. Place that into the machine. The sound was obviously air going into a vent it, and then we'll pump it. So press the pump button, we'll go through a pump sequence.
And this is just sucking all the air out of the thing?
That's right, just sucking out the air of the machine. It will get down to a reasonable vacuum, probably in the 10 to the minus 5 millibar range, and then we're allowed to get the electrons going down the column. It takes about 2 or 3 minutes to do so, so you can then sit down and find out where things are.
As Katie mentioned earlier, air is not a good conductor of electrons, which is great to avoid constant electrocution, but a challenge if you want to actually send electrons onto a sample to image it. In order to make sure the electrons reach the sample, we needed to pump down the chamber into a vacuum. While we waited for this to happen, we asked John a bit more about how the microscope actually works.
The principle of the electron microscope is we have effectively a small accelerator unit at the top of this electron column. So we generate electrons and we accelerate them up to fairly high energy, say between 5 and 30 kilovolts, about 5,000 and 30,000 volts. And they're then focused through a set of electromagnetic lenses. And they're quite analogous to the lenses, optical lenses in a conventional benchtop optical microscope.
The limitation of any kind of imaging technique is the resolution we can have. When we use light, we are limited to resolving features that are bigger than the wavelength of that light, which means we can really only see down to about micrometers scale. That's 1/100th of the width of a human hair. But electrons have much shorter wavelengths, so we can see down to nanometers, which are thousands of times smaller than that.
The way we produce the image is to focus a pencil beam of electrons onto the sample and scan the beam across the sample. And as we're scanning, we monitor the various signals that come off the sample.
When electrons hit a sample with high energy, they send a ripple through the atoms on the surface of that sample. This shakes up electrons within the sample and sends some of them back up from the surface. It's a bit like firing a high-powered hose into a swimming pool and watching the water splash back up.
By measuring the intensity of these generated electrons and then modulating that according to where the position we are on the sample, we get actually very, very intuitively clear image of the sample we're looking at.
We waited for the chamber to pump down to a vacuum before we could fire up the electron beam. There was a small camera so we could actually see inside the chamber while this happened, and as our 2 or 3 minute wait turned into 10, 20, 30 minutes, we noticed that the bee started to bubble. It turns out our bee had recently drunk a lot of nectar which was still in its stomach. It was going to take a while to pump a bee full of nectar down to a vacuum, so we decided to take it out and chop its head off, which was professionally done by Hamish, and just have a look at the bee sting. As we turned on the electron beam, a black and white image of a bee sting started to flicker onto the screen, and Hamish explained what it was we were seeing.
Ooh. Wow.
Oh, cool. Yes, you got the barbs. Brilliant. Okay. So those things there are backwards pointing barbs, and that's how it sticks in you. This is a worker honeybee. And worker honeybees, when they've got their sting in you, it actually, when they fly away, they leave the stinger there. So the bee will die after it's stung you. That's only the case with honeybees. And what we can see here is the reason for that. We've got these little backwards pointing barbs on the end of her sting. It's a bit like a fishhook. You push it in very nice and easily, but when you try and pull it out, it won't come.
So certainly a new way to look at a bee sting. You heard from Adam Murphy, John Walmsley, Simon Griggs and Hamish Symington.
And if you want to know what that bee sting looks like, then head over to our Instagram @NakedScientist to take a look. So we promised at the start of the show to take you on a spin around the Electron. And whilst we've had a whistle-stop tour, spin is in fact a physical property of the Electron. But what exactly is it and how is it useful? Russell Coburn, a physicist from the Cavendish Laboratory in Cambridge, joins us in the studio to tell us about his work on spin. So Russell, start at the very beginning. What is spin?
To really understand spin, we've got to look at quantum mechanics. But to get a rough idea, if we think of an atom as being a central nucleus, positively charged, with the electron going around the outside, just as like a planet going around the sun, then the spin is as if the planet is spinning on its own axis as it revolves around the sun. So just like the Earth does, in fact.
And so how does spin affect electrons?
Well, in many materials, in many atoms, you have as many spins pointing up as you have spins pointing down. In other words, some electrons are going clockwise on their own axis and some are going anti-clockwise. But in certain materials, particularly materials like cobalt and nickel and iron, there is a residual spin left over, and that gives the materials very dramatic properties. It's a property that we know as magnetism.
I see. So most other elements, their spins will cancel out, but in magnetism it's because you've got that little bit left over.
That's right, and they're all spinning in the same direction. And it can be very powerful. If you think of a fridge magnet, it's holding itself up against its own weight, against the gravitational force, and that's all because of the spin of those electrons.
Now, this is something that you work in, not specifically magnets, but how is spin useful to you?
Well, one of the things that scientists and engineers have been thinking about for a few years now is whether we can take microchips, which work using the electron, and whether we can start to make use of the spin of the electron. So most microchips today only use the charge property of the electron. But if we could use the spin as well, that gives us a lot more levers we can pull to design fun new devices.
Oh, how so? What sort of devices are we talking?
Well, one of the things you'll know is that a light bulb needs electricity to give out light, but a bar magnet is still magnetic even without any power source. And so the idea is that maybe we could have chips that could do things, have some sort of functionality, even if they don't have a power source, which would be great for mobile devices or places or low energy computing.
And is this something that you're working on?
I've done a lot of work on this in the past, and it's even at the stage now where you can buy these things. So you can buy spintronic chips just as you can buy conventional charge-based chips.
And what are some of the other applications that we could use this on of side? Can we use this, say, in health?
Yes, so one of the ideas that my own group in Cambridge is looking at is whether we can make very sensitive detectors for some of the molecules that are associated with cancer. So we are trying to develop a very simple chip, a bit like a pregnancy test kit, that you could splash urine on, and it would tell you very quickly and very accurately whether any of the molecules associated with kidney cancer, for example, are present, to act as an early indicator of the disease.
And how does that actually work?
Well, there are these molecules that are excreted at very early stage of the disease, at a stage where it's still possible to cure the disease with a very high success rate. And we have ways of detecting them, but they're very difficult and expensive ways. So we're trying to use our spintronic chips to do the same thing, but in a low-cost, portable form. Biochemists know how to identify biomarkers. They can use antibodies, for example. And when those antibodies identify a particular biomarker, they give out a little flash of light. Part of the problem, though, is interpreting that light, working out which biomarker it is which is present. And if we combine the biochemistry with a little spintronic device, we can work out which one it is, and from there we can begin to build a picture of which biomarkers are present.
So where does the magnetism come into all of that process?
So the magnetism allows you to move your particles around. So we have little particles which are effectively portable chemistry labs, and that's where we're looking for the interaction between the biomarkers and antibodies, but we need to be able to move them around so that we can test them. And a magnetic material is a great way to do that because, as we mentioned before, you get very strong forces. Think of the fridge magnet, and that allows us to actuate, to move the particles around. It's slightly more complicated than that. If you just use a conventional lump of magnetic material, just a lump of iron, what you'd find is that everything just sticks together. What you need is smart material, and you can only get smartness by bringing in full-blown spintronics.
You mentioned cancer detection there. Is there any way that spintronics can be applied to treatment then, on the other side of the coin?
This is something else we've been working on. So we partnered with oncologists at the University of Chicago, and we made some little microparticles out of spintronic materials, and we inserted them into cancer tumours, and we caused the particles to start vibrating. And what we're trying to make is a chemotherapy where the toxicity can be turned on and off by remote control using a magnetic field.
And are there things that we can do with spintronics that we can't do with electronics?
So one of the dreams that physicists have at the moment is whether we could invent a completely new architecture, a new design of chip. At the moment, most computer chips follow the same design strategy, and it's very different to the way, for example, the human brain is architected. And people have thought for a long time, could we design chips that mimic the structure of the brain? And if you only have charge-based chips, then the answer is no. But if you have spin-based chips, if you have spintronics, then maybe we could do that. Maybe we could make magnetic brains.
Well, that sounds really exciting and almost sci-fi-esque. Russell Coburn from the Cavendish Laboratory in Cambridge, thank you very much. And thank you to all our other guests this week. Katie Duncan, John Walmsley, Simon Griggs and Alex Tom. And Keita and Urban put the show together.
And we've just got time for Question of the Week. Emma Hildyard's been pondering this question from SOGAT.
What is the exact cause of monsoon rain and how will it be affected because of the global warming?
We put the question to our forum and the answers came flooding in. Flummoxed said that global warming would warm the oceans and put more moisture in the atmosphere. We asked Ruth Geen, who's a mathematician from the University of Exeter, who works with modelling the effect of climate change on monsoon seasons.
So this year we've seen some strong monsoon rains in parts of South Asia, which have caused these terrible floods.
Britain is well known for its rain, but we don't get big tropical storms that are typical during monsoon seasons over the land of the tropics. But why is this?
It's all to do with the latitude we live at. The main driver of the monsoons is the sun. In the tropics, the sun is almost directly overhead in summer. This heats up the ground of the Earth and the air above it. This hot air begins to rise and the atmospheric pressure over the warm region falls. The pressure difference between the hotter air over the land and the cooler air over the ocean causes the prevailing wind direction to change, bringing warm, moist air over the land.
When the humid air meets the hot air, the water vapour begins to condense and releases rain.
The amount of monsoon rain that falls varies from year to year, and this depends on a mix of different factors, like sea surface temperatures in the Pacific and Indian Ocean.
The amount of rain and where it falls varies with a given season too. This is affected by intra-seasonal oscillations, so there's a lot going on.
Over the 21st century, climate models suggest that monsoon rainfall over South Asia will increase, perhaps by around 5 to 10%, though it's worth noting that there's a spread in what the models predict. Some suggest more than this, some less. Climate change is causing the temperature of the air to gradually increase, and warmer air can hold more water vapour.
This more humid air is expected to cause more rainfall during monsoon season over the land of South Asia.
If a larger volume of rain falls over a given period that can be drained to the rivers, or than the river can carry, then this causes flooding.
However, this rainfall is vital for the growth of crops, and a weak monsoon season can lead to crop failures.
While we've seen the floods in the west of India on the news this year, in other regions, such as Chennai in the southwest, there's actually a drought. While in the long term, models suggest monsoon rainfall will increase, over the last 50 years there's actually been an overall decrease in Indian monsoon rain, but an increase in the extremes of rainfall that cause drought and floods. Unfortunately, these extremes are also predicted to become more severe in future. So, while more total rainfall could possibly be positive for agriculture, More intense wet and dry periods would result in more floods and droughts.
Thank you, Ruth, for shining a little bit of light on that. Next week, we'll be answering a question from Bill.
My question is about Chernobyl and why it is that wildlife seems to be thriving there, and yet we understand that humans still can't survive in the area.
And if you think you know the answer, you can email chris@thenakedscientist.com. You can find us on Facebook, tweet @nakedscientists, or join in the debate on the forum, thenakedscientist.com/forum.
Next week, we're answering your science questions with a Q&A, so do send them in to us. Casey's just given you the email, but if you missed it, it's chris@thenakedscientist.com.
The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Katie Haylor.
I'm Izzy Clark.
And thank you for listening. Goodbye.